Today we start section 6.2, where we talk more about the normal distribution and also about something called the standard normal distribution. So it turns out that these normal distributions may vary from one another in a couple different ways. The mean, mu, may be located anywhere on the x-axis, and the bell shape may be more spread out or less spread out depending on the size of the standard deviation, sigma. So these differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specified interval of x values. We use the area to determine the probability that a measurement will fall into that interval. So I mentioned a little bit before that we need the area under this normal curve to be exactly 1, because we're going to use that area to answer probability questions. And the sum of all the outcomes in a sample space, the sum of the probabilities of all the outcomes in a sample space, has to also be 1. So to see what this means, we've got a number line right here. So just think of this as a real number line. And so let's say right here, let's say this is 1.3 on the number line. And in this case, we've got a bell-shaped curve here. And it's kind of a pointy curve. Let's say this represents 1.3 ounces. So this will be the mean. So we've got a normal distribution. So the mean is right here. So that's the peak. And let's say, let's call this, let me do it this way. Let's call this, we'll say this is mean 1, because we're going to look at other ones. Let's say standard deviation 1 is 0.1 ounces. And let's say that this is the weight in ounces of field mice. So we have this distribution like this, and we may need to know how these weights of field mice are distributed, so that if we study field mice in a certain region, maybe like in Chernobyl, where now scientists are studying plants and animals in that area to see what the effects of nuclear radiation is. So maybe we are studying field mice, and we know the breakdown in weights of field mice of that species, and then we can look at the breakdown of the mice in that Chernobyl area and see if it follows this. So we could have some distribution like this. So here's a number line, here's 1.3. Later on, farther up the number line, here's maybe 8. This would be mean 2. I just leave the units off. Let's say this is 8. But let's say this doesn't have units. This is just 8. Let's say standard deviation 2 is 1.2. And so it's a bigger standard deviation. It's maybe more spread out. And maybe this is the number of mistakes per week made by vending machines and let's say at GRCC. And this one came up because of the worst day ever that I had since I worked here. Maybe you guys can relate to this. So one day I was super thirsty. Luckily had a couple dollars in my wallet, which when you have kids, you know that's kind of a rare event. So I'm thinking, oh my gosh, it's my lucky day. I'm gonna run up to the vending machine and get a nice cold Coca-Cola to go between my classes. So I run up to the vending machine, super excited, put the $2 in there, press the button. Now you might think the worst thing that could happen is nothing comes out, but no, that's the second worst thing that could happen. Here's the worst thing that could happen. I'm sitting there excited, I can hear it banging around, bang, 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 it's coming down, boom, comes out at the bottom, thinking, yes, I'm so thirsty, you reach in and grab it. It's not a Coca-Cola, it's a Diet Sprite. Diet Sprite, who would do that? Who would put that in the Coca-Cola area? In a Diet Sprite, I don't know what you even do with a Diet Sprite. There's nothing in there. I opened it up. There's no flavor. There's no caffeine. All I could find in there was sadness. It was a terrible day. And that's where this came from. So this one's at 8, and then maybe, move down the number line here. Maybe this is 27.2. No, this is not to scale. I'm just writing these things to get the idea here that these could have different shapes. This one's a little more spread out. Maybe it goes like this. And this would be maybe the age of GRCC students. And I'm just making these numbers up. Basically, the idea is this. These all have their different spots on the number line where the means are, right? And they have, they're spread out differently. This one's kind of tall and skinny, and they have different spread based on the standard deviation. So we're going to have to do things like figure out the area under, say, this curve from here to here. For financial aid reasons, we may need to know the likelihood that a student getting financial aid is in a certain age group. So we're going to be having to figure out areas under these curves, and what you don't want to do is have to do this for every conceivable combination of mean and standard deviation, because to find these areas, like I mentioned earlier, it takes multivariable calculus. So you would have to have at least a Calc 3 student along the way to calculate all these, and they're not easy calculations. They take a while. So what happened in the past is we took all of these and we standardized them. So we're going to take, no matter what kind of normal distribution you have, any kind of bell-shaped curve, meaning it will have there could be different combinations of mean and standard deviation. So regardless of those combinations, we standardize them all. So think of it as squeezing these all together into one standard normal distribution. So each of these is a normal distribution. What we want is a standard normal distribution. So we're going to standardize these. So at that point, what would happen before the mid-90s or so, we would have a table of values. So you'd have a table of values, and you would standardize each of these so that you could use that table of values for each one of these. So on the way to doing that, we are going to be introduced to something called the Z-score. And Z-scores are really useful. So even though modern calculators could figure these out for each category, it still is nice to standardize these so we get the Z-score, because the Z-score is really important. So we still standardize all of these, even though we don't use tables. At least for the most part, we don't use tables. But the concept is the same. We want to have a standard way to do this, so we'll get Z-scores. And also, some calculators can still only do this if it's standardized, although the TI-83 and 84 can calculate things without standardizing them first. But so that's what we're going to do in 6.2. We're going to take these normal distributions, any normal distribution, and we're going to standardize it. So here's the reasoning. So it would be impossible to create a table of areas under the normal curve for each different mean and standard deviation combination, right? For each mu and sigma combination. So we need a way to standardize the distribution so that we can use one table of areas for all normal distributions. We achieve the standardization by considering how many standard deviations a measurement is from the mean. And we'll find out this is actually called the z-score. This allows us to compare a value in one normal distribution with a value in another different normal distribution. So what we just talked about there, we're going to find out how many standard deviations a measurement is from the mean. And to do that, we basically use this concept of z-scores. So the z-score, there's different ways of saying this also. Z-value, standard score. I almost always say z-score. Our book says z-score probably most of the time, but it also refers to standard score. It's the same thing. It means you're standardizing this. So the z-score gives the number of standard deviations between the original measurement and the mean of the distribution. So to find the z-score, you take x. So now x is going to be the original raw data, or what they call the original measurement x. So we take the data point, subtract the mean, and then divide by the standard deviation. So be a little careful with the order of operations. Make sure you do this first, or you could put this in parentheses, then divide by the mean. All right, so you don't want to go in your calculator x minus mu divided by, because it's just going to divide mu by sigma. So you want to go x minus mu, enter, right, and then divided by sigma. So basically what's going to happen is all of these up here, all normal distributions, are going to merge into this, what's going to be called the standard normal distribution. In the standard normal distribution, take a look at what's happening here. For the standard normal distribution, you have right here, right in the middle of it, the mean is 0. So when you have a data value that is one standard deviation above the mean, that means it's got a z-score of 1. So all of these refer to what's called z-scores. So it comes from this formula, the z-score. So looking at the z-score, what if you had a data value that was exactly the same as the mean? So if your data value was just an average value, it was the same as the mean. You take your data value, subtract the mean, but since they're the same, you get 0 right there, right? You get a 0. So when your z-score is 0, you're exactly average. You're right in the middle here. So when you take a raw data and you convert it to a z-score, if you get 0, it means it's average. If you get a positive z-score, that means it's above average. If you get a negative z-score, it's below average. And if you've never done this before, it'll make more sense in a second here when we look at our own z-score for height. So we still have, even though this is a standard normal distribution, the area under the curve is still 1. But it's just set up in a way where the mean is 0 and the standard deviation is exactly 1. That's what will happen when you standardize the normal distribution. So just to make sure, so these are what's going to be called z-scores. So we're going to figure out our z-score for our height. So if it turns out that you have a z-score of 2, that means your height is 2 standard deviations above the mean. If you have a z-score of -1, it means your height is 1 standard deviation below the mean. If you have a z-score of 0, that means your height is the mean, right? Because then your height minus the mean would be 0. So we've got this little table from 6.1, and it gives the heights in inches of males and females in the U.S. So we've got men and women here. Got the mean height and then the standard deviation. So what we want to do is figure out our z-score. So z equals x minus mu over sigma. this is a formula that we'll use a lot in chapter 6. You'll end up probably memorizing this without even trying because you use it so much. X minus mu divided by sigma. So take a second, just figure out your z-score. And know that 99.7% of the time you're going to get a z-score between -3 and +3. Right? Remember we talked about in 6.1? Around 99.7% of the data points will fall within 3 standard deviations of the mean. There's 6 to 8% of us will get a z-score between -1 and +1. And 95% of us will get a z-score between -2 and 2. So go ahead and find your z-score. And then we will also look at a couple more. So remember, whenever you need to, just press pause, figure something out, and then press play again. So z-score of a female student who is 68 inches tall. Okay, so for this student, we would have z equals 68. That's her raw score, right? That's her height, 68 inches tall. Now look up above here. So for a woman, 63.7 is the mean. So I go x minus mu, right? That's mu. So I go 68 minus 63.7 divided by 2.8. So remember, you want to do this first. 68 minus 63.7, enter, then divide by 2.8, right? Make sure you hit enter first. And if you do this correctly, you'll get about 1.54. So this student is about 1.5 standard deviations above the mean. So this student is taller than average, right? Positive z-score means that this person is taller than average. They're about 1.5 standard deviations above the mean. So now let's do the same thing for a male student who is also 68 inches tall. So z equals 68 minus, now this time the mean for a male is 69.3. Go 69.3. Standard deviation is the same for both. And we get about -0.46. So what's the significance of the negative? Well, if you look at this, if x is smaller than mu, we're going to have a small number take away a large number, we're going to get a negative, right? So when your z-score is negative, it just means that this data point is below the mean, right? The mean is 69.3, so 68 is less than that. 68 is below the mean, so the z-score will be negative. So when it comes to z-scores, a data point with a z-score of 0 means it's the average data point. It is the same size as the mean of all the data. And again, this is only for data that comes from a normal distribution, which there are many things that follow the normal distribution. So if you are sampling from data that follows a normal distribution, then these z-scores can be used. A positive z-score means that data point's larger than the mean. Negative z-score means it's smaller than the mean. And now I want to find a z-score that would be called an outlier. So usually in class we'll have some Pistons fans, and I'll ask somebody from the Pistons and the height of somebody from the Pistons. So because I want to get an outlier. So I just looked online, and there's somebody named, looks like Thon. Whoops, let me get this here. Thon Maker. He is 7 feet tall. Okay, so 7 feet, 7 times 12 is 84. Right, so he's 84 inches. So let's find the z-score of this guy so we can talk about what an outlier is. So this basketball player is 7 feet tall, so you go z equals 84 minus 69.3 divided by 2.8, and you should get 5.25. So 5.25 is a extremely unusual z-score. It's extremely unusual. If you get data that has a z-score of 5.25, that's the kind of data you kind of have to double check to make sure that there wasn't a mistake. So think of a z-score of 5 in the same way you would think of if you're just going about your day, your day-to-day life, not going to basketball games, but just going about your day-to-day life. How long would it be until you ran into somebody who's 7 feet tall? I mean, just think when you're in the store, in the mall, or whatever, you don't see very many people 7 feet tall, right? So that's going to be like a z-score of 5.25. Just think of 7 feet tall, z-score of 5. You don't see either one of these very often. So it's really unusual to get z-scores beyond 3 or in the other direction beyond -3. So an outlier, by many definitions, is this. There are a few different ways to define an outlier, but a pretty good definition that is fairly standard is 2.5 standard deviations from the mean. Okay, so it's 2.5 standard deviations from the mean. It's not super unusual, but it's starting to get out there. So this is kind of our magic number for outliers, 2.5 standard deviations from the mean, which means a z-score, right? This is like a z-score of 2.5 or -2.5. So this is, easily an outlier by any definition. So when you guys found your z-score here, probably almost everybody was between -3 and 3, right? 99.7% of us will be. So if you had a height of -2.5 or +2.5 or more, then that just means you are an outlier. Just means it's a little unusual. So let's see. So we'll go with this definition, 2.5 standard deviations from the mean, above or below, and just associate this, like when you get an outlier of 5, it's extremely unusual. So when we get out like beyond a z-score of 3, kind of in unusual territory. So the standard normal distribution is one where you have a mean of 0 and a standard deviation of 1. So we take these normal distributions and we standardize them. So it's standard normal. So we've got the mean right here of 0, a z-score of 3 or -3 is getting out there a ways, right? An outlier would be like 2.5 or -2.5. And then there's just say on page 291 of the book is a better picture, but basically we could see that 68% of the data is within 1 standard deviation of the mean. So this in here, 68% of the data. So these numbers still hold just like before. Okay, so by the time you get out to here, when you get to 2 standard deviations from the mean, you are going to get about 95% of the data. And when you get out here, 3 standard deviations from the mean, or in other words, a z-score of -3 to 3, 99.7% of all the data will be captured between a z-score of -3 and 3. So when we figured out our height above in the notes, 68% of us had, or around 68% of us would have a z-score between -1 and 1, 95% between -2 and 2, and 99.7% between -3 and 3. So what we've done is we took normal distributions, which can have any mean and any standard deviation, and we standardized it. So once you standardize it, then it has a mean of 0 and a standard deviation of 1, and the area under the curve is still 1. Okay, so everybody should get these next two questions correct. A positive z-score means the raw score x is it above the mean or below the mean? Remember, the raw score is the original data. If you get a positive z-score, it means the original data is above the mean, right? Positive z-score, it's above the mean. What about a negative z-score? That means the raw score x is below the mean. Sometimes we'll need to convert from a z-score to a raw score. So remember, the book will sometimes call a z-score a standard score, and the raw score is just the actual data point, x, right? So to do this, we can start with our formula. So you start with z equals x minus mu over sigma. So this is formula that we have when we have the raw score, and we plug in the raw score here, and we're looking for the z-score. But in this case, you want to manipulate this equation so that it's solved for x. So some of you will be very excited here. We get to do a little bit of algebra. So if you're in algebra class and you've got this equation and you're solving this equation for x, right? So right now this is an equation. We know it's an equation because there's an equal sign, and it's solved for z. But we want, instead, we want it to be solved for x. We want it to say x equals something. So what many of you learned from algebra is if you have a equation with a fraction, you can get rid of the fractions by multiplying each side of the equation by the denominator. So multiply each side of the equation by sigma, which makes this cancel here. So then we get z times sigma equals x minus mu. And then we want to solve this for x, so we just have to add mu to each side. So you go plus mu on this side, plus mu on this side. That's going to go away, and we'll get z sigma plus mu equals x. Or if you just reflect that equation, we get x equals z sigma plus mu. So this is another equation we'll see quite a bit. We'll use this original equation more often, but this will come up too. So this one is when we want the raw score, but we have the z-score. So we just plug in the z-score here, multiply by the standard deviation, add the mean, and we'll get to the raw score. Then we've got a note here, and here is the note. It just says this: any normal distribution So remember, this normal distribution, a bell-shaped curve, that can be used to model all kinds of situations. And any one of these, any normal distribution at all, can be converted to a standard normal distribution. By converting all the measurements to z-scores. So here we've got a normal distribution, bell-shaped curve. Mu could be anything at all, sigma could be anything at all, and we convert it to a standard normal distribution. Now remember, the standard normal distribution is this very special normal distribution where the mean is 0 and the standard deviation is 1. So when you see that you've got a standard normal distribution, it's still a normal distribution, but it's been standardized in such a way that the mean is 0 and the standard deviation is 1. So any normal distribution at all can be converted to this standard normal distribution by converting all the measurements to z-scores. And in the back of the book, when you look up a table for the normal distribution, you'll see this one for the standard normal distribution, because this one can be used for any normal distribution as long as you convert the measurements to z-scores. One thing too, make sure we're correct with the terminology. Again, the details are going to be important here. There is a such thing as a normal distribution. There's such thing as a standard normal distribution, but there is no such thing as a standard distribution. So make sure you don't say standard distribution. There is no standard distribution, right? This phrase or this term standard in this context is referring to this normal distribution being standardized, right? So we've got a normal distribution, and then we've got a special case of this, a standard normal distribution where the mean is 0 and the standard deviation is 1. But there's no such thing as a standard distribution. Okay, so we've covered some information, and now to really learn this, we're going to have to go over some homework problems so you can see how all this works. You've got a calculator command we've got to learn about. So let's take a look at some of these homework problems. So the first one is from the homework from section 6.2. It's on page 297, and it's number 6. And it says we've got a normal distribution. So as soon as you hear this, as soon as you know that you're working with a normal distribution, you know something about the data. You already know that it's going to look like a bell-shaped curve. And you know how the data are even distributed, right? You know that here's the mean, whatever it is. And you know that if you mark off standard deviations along the number line here, you know that roughly 68% of the data are going to be within one standard deviation of the mean, right? As you go further out, you know that in here you're going to get about 95% of the data. If you go even further out to 3 standard deviations from the mean, you're going to get about 99.7% of the data. So as soon as you see this, as soon as you see it's a normal distribution, you know actually quite a bit about how the data are distributed. And just like in nature, you're not going to find a perfect sphere, right? You'll find maybe some pebbles that are spherical. Well, in distributions in the real world, you don't find ones that are perfectly like this, right? But you find data that fits this really, really well enough where we'll say the data are distributed normally, or the data follow a normal distribution. So when you see this, you know that these numbers are going to be pretty close. So for number 6, they tell us we have got a normal distribution with a mean of 10 and a standard deviation of 2. And then for A and B, they want us to find z-scores corresponding to x values. And remember, an x value would be the raw score, the original data point. And C and D, they want us to find a raw score corresponding to z-scores. So these are going to come down to using this formula, or the other version of it where you're solving for x. All right, so these two formulas. And we'll talk about the Chapter 6 handout at some point, maybe after section 6.3. The Chapter 6 handout has both of these formulas on here. So go ahead. Let's have you guys take a second. If we were in the classroom, we would do these have you guys come up to the whiteboard and put your solutions up. Let's have you try A, B, C, and D, but try them first. Press pause and try them, and then come on back. So for part A, we want to find the z-score corresponding to x equals 12. So I'm looking for the z-score, so I need to use this formula. This is z equals, right? Now you can actually use either one of these. You could use this one if you wanted to. It's just this one is already solved for z, so it'll be easier. Algebraically, there'll be less steps. So I'm looking for z, so I use this one. Z equals, and I just plug in the numbers. X is 12. So I'm going to use that formula and get z equals 12 minus 10 divided by whoops, not divided by sigma, divided by 2, right? Because this is given for number 6, the mean and the standard deviation, so I just plug these in. Then you just do the math, so you get 2 over 2 or 1. So for part A, a raw score of x equals 12 for this set of data here corresponds to a z-score of 1. So a z-score of 1 means that this data value is 1 standard deviation above the mean. And we can see in this case it's really easy to see that it is, because 12 is 1 standard deviation above the mean, right? 10 plus 2 is 12. So for part B says x equals 4. So before you even start this one, just think of this. Is z going to be a positive or a negative number? And we can see because this data value is less than the mean, so the z-score is going to be negative. Just like this data value is more than the mean, so it's going to be positive. So we do the same thing. We just plug this into the formula. We get 4 minus 10 over 2, negative 6 over 2, which is negative 3. So when you get a z-score of negative 3, this would be considered an outlier, right? It's 3 standard deviations below the mean. So z-score of negative 3 means you're kind of getting out there. When you get a z-score around 2.5 positive or 2.5 negative, you're kind of getting out there a little ways. So this would be considered an outlier. So part C says, find the raw score corresponding to z equals 1.5. When I'm looking for the raw score, so this formula will be easier to use. You can still use this one. Again, it's just easier algebraically to use this one because I'm looking for x and this one is already solved for x. So I'm going to use this one and say x equals z times sigma plus mu. So we get 3, I don't know why I keep doing this, plus mu, and mu is 10, right? I'm using this formula with this z-score and these values for mu and sigma. So this would give us 3 plus 10 or 13. And you can see it kind of makes sense, right? This z-score is a positive. It's a positive number. Z equals 1.5. So I know that we're going to be above the mean, right? It's a positive number. A positive z-score corresponds to a number bigger than the mean, and that is bigger than the mean. And then finally, part D says z equals negative 1.2. I want to find the raw data that corresponds to this z-score. Well, this is a negative z-score, so I know that my raw data, when I get it, the x is going to be less than 10, because it's a negative z-score. And we just go ahead and we go x equals z times sigma plus mu, negative 2.4 plus 10, which gives us 7.6, which we can see it is smaller than the mean. The mean was 10. So for number 10, we're going to work with these x intervals and convert them to z intervals. And it's going to seem kind of strange right now, but it'll make complete sense in 6.3. They're just getting us ready for something we're going to see quite a bit. So number 10 says, they're talking about these fawns, these young fawns. They have a body weight that is approximately normally distributed. And again, that's just another way they can say it. Nothing is perfectly normally distributed, right? Nothing in reality. So when they say approximately normally distributed or it is normally distributed, it all means the same thing. It means that it's close enough where we can use all this material that we are learning in Chapter 6. We can use normal distribution table and all the commands we're going to learn about the calculator. So it says talking about body weight, actually mass is what I guess it should say if you're using kilograms, but they've got a mean of 27.2 kilograms and a standard deviation of 4.3 kilograms. And it says let X be the weight of a fawn in kilograms. They want to convert the following X intervals to Z intervals. So for something like this, let's go to this part A. It says X is less than 30. So they want us to not say X is less than 30. They want us to say Z is less than something, a Z-score. So all we want to do is we're going to rewrite this. We're going to say Z is less than, and we don't want the raw score of 30. We want to convert it to a Z-score. So we do just basically what we did in the problem above here. We want to find the Z-score that corresponds to X equals 30. So we go back over to this formula that we've seen before. We're looking for a Z-score. We use this for the X score, 30, minus the mean, which is 27.2, divided by the standard deviation of 4.3. And so you go through here, and if you do the math, you should get 0.65. And I rounded it. It's like 0.651163, but I just rounded to the second decimal place to get 0.65. So then what we write here is Z is less than 0.65. And what we've got is an X interval, and we change it into a Z interval. And we'll do this a lot starting in section 6.3. And one thing they could do also for something like this is make a compound interval. So for instance, for part C says 32 is less than X is less than 35. Well, this is an X interval. It's an interval based on X. They want a Z interval, so we just need to convert both of these to Z scores and put a Z here. So for the Z interval, we would have Z instead of X. We still have the same inequalities. Then we just need to one at a time convert these to Z scores. Again, using this formula up here. So for 32, we have Z equals 32 minus 27.2 over 4.3. So when you do that, we get about 1.12. So we have 1.12 is less than, this Z's a little sloppy looking. I'm going to fix this. Is less than Z, which in turn is less than, and we have this other Z score. Now you can see that both of these Z scores are going to be positive because they're both bigger than the mean. When you do this, you get about 1.81. So we have this X interval and we converted it to a Z interval. Also, make sure you do these problems along with me. So you notice with this one, the answer is 1.116279. Keeps on going. So rounded to the second decimal place. So you can't just like lop off the number there and put 1.11. We want to use rounding, so we want 1.12. So just always kind of keep rounding in mind, where you can round where you want to, but we would need to round correctly. So number 20 is where it's going to start to get a little interesting. So on this one, I'm going to show you how to use the normal distribution table, because this table is, even though almost everyone will use your graphing calculator, this table is a good one to know how to read, because there is another table that we actually have to use that is very similar to this one. So I'm going to show you how to do this one on the table first, and then I'll show you how to do it on the calculator. And for questions about standard normal curves, we'll almost always use the calculator. So what this 20 is talking about is the area under the standard normal curve. So remember, it's not just a normal curve, It's the standard normal curve. And when they say curve, they just mean the graph of the standard normal distribution. And these are used pretty much interchangeably. So we're studying the standard normal distribution. The graph of that distribution is the standard normal curve. And it's just a bell-shaped curve. But of course, the standard normal, not just the normal curve, but the standard normal is special in that the mean is 0 and the standard deviation is 1. So you have these z-scores going out here. And with the normal distribution, or the standard normal distribution, it's the same. Within 1 standard deviation of the mean, we're going to get 6 to 8% of the data. Within 2, we get 95%. Within 3, we get 99.7%. So here's what they want us to do. They want us to find the area under this curve to the right of this z-score. Well, first just keep in mind, what's the area under the curve, the entire curve? It's exactly 1, right? So they're asking us to come over to 0.15, so just to the right of this 0. And they want us to find the area here. They want us to find this area. Well, had this said to the right of z equals 0, just plain old 0, then it's the easy question, right? The area there's going to be 0.5 and 0.5 on the other side. But it's not exactly there. It's 0.15, so we're over here a little bit to the right of that. So we know our area is going to be a little bit less than 0.5, but how do we find it? So this is standard normal curve, and you've got one for most of your textbooks, there'll be one in the inside front cover. There's also one in the back. In the back, it's table 5A, and it's appendix A22. So there's at least 2 of them in the book. And the way that these work is this. So it says the area of a standard normal distribution. You notice it's got all these negative z-scores here. These are the z-scores, all negative. Here's all positive. And our table is called the left-tailed table because it's got the area to the left. So the way this works is your z-score here. If you look up a z-score, and you can get the first decimal place, or the first decimal place here, and the second one here. And then the area is to the area to the left of that z-score. So you can see right here, negative 0 is the same as 0. The area to the left of a z-score is 0.5. And same thing over here with the positive 0 because it's the same. So for us, we have, for number 20, it says to the area to the right of z equals 0.15. Well, so here's what we're going to have to do. Think of what we've got here. We are looking, so here's 0, and we've got this 0.15 right next to it. We want to find this area here on the right, but the table won't do it. Our table is a left-tailed table, which is pretty common. So our table will give us the area here to the left of the z-score, but we know that if we add these together, we have to get 1. So what we need to do is look on the table for z equals 0.15. So to do that, the first decimal place will be here. So we look for 0.1, which you've got it right here. Then the second decimal place is up here. So we want to go to 0.15. So we go over to 0.1 and up to the 0.05. So this number, 0.5596, that's the number that represents the area to the left of z equals 0.15. So z equals 0.15 is the z-score right here, just to the right of 0, 0.15. And the area here is this number right here, which is 0.5596. So we know that basically this area here is 0.5596, and we want to know this area, right? So the thing about the table that we've got, and most of them are like this, it's a left-tailed table, right? The shading is on the left. So whatever z-score you look up, it's going to give you, these numbers here represent the area to the left of that z-score. So the book wants to know the area to the right of 0.015, but we can only find the area to the left. But once we have that, we can easily find this, because if we add these together, we have to get 1. So this thing to the right is just going to be 1 take away this. So this area here is just 1 minus 0.5596, which ends up being equal to 0.4404. So that's what our answer is. So this is how you use the tables. I just wanted you to be able to read them. And you notice that the z-scores only go to negative 3.4, right? That's the farthest negative they go. The farthest positive they go is positive 3.4. We will talk about this later on. This little box here will be important for us later. But now what we'll do is we'll see how to do this on the TI-83 or 84. Okay, so we looked at one way to do these. One way was, I'll do it like this, 20. One way is to use the table, and this is the little picture we drew from the table, left-tailed table. The other way, and this is the way that most of us will do, is we use a calculator. And we have a command called normal CDF. And it has an input of lower bound, upper bound, mu, and sigma. So if you guys remember, when we used binomial CDF had that weakness of it had to start at 0. Normal CDF doesn't have that. Normal CDF says, you tell me where to start, lower bound. Tell me where to stop, that's the upper bound. And then mean and standard deviation. But these two are actually optional. So these two are optional. So if we were going to do this problem on the calculator, what we would do is this. I'll show you where normal CDF is. We go normal CDF. Lower bound, well, this is an actual number line. So we want to have the smallest number first. That's the lower bound. This is going to be the number always on the left. And in this case, that number is 0.15. So you can just put 0.15. Then we need the upper bound. Well, the upper bound really is infinity, because if you think about, in reality, this number line goes forever, right? It goes forever. It goes from negative infinity all the way to positive infinity. But our calculator doesn't understand what infinity means. So what we can do is just we don't have to put a huge number like 1 billion, because these are z-scores. If you remember when we talked about the Pistons basketball player, he had a z-score of around 5, and that's like a really, really unusual height of a person. So if you put a z-score of 10, like when it comes to z-scores, a z-score of 10 is, as far as our calculator is concerned, it might as well be infinity, because although technically this curve never crosses the line, by the time you get out to a z-score of 10, this curve is so close to the line that our calculator can't tell that it's not touching. The gap is too small for our calculator's memory to even handle. So for us, when we have infinity, we can just put 10. A z-score of 10 is such an outrageous z-score that if you put anything bigger than that, it won't change the answer on the calculator. So our calculator doesn't know what infinity means, but a z-score of 10 might as well be infinity. So that's what we'll do here for infinities on our calculator, just put 10. And you'll see, you don't really even need 10. Most of the time, probably 7 or 8 would be good enough. But 10 is just an easy number to remember, so I just always use 10. If you put anything bigger than that, it won't change your answer. So 10 is just a good one to remember. These are optional. When I just hit, if I just close this now and ignore those two, it's going to assume, it's assuming that this is 0. It's assuming that this is 1. Whoops, that sigma is 1. Because it's assuming that these are from a standard normal distribution. So you can just leave them blank and it will insert a 0 and a 1 here. So we just type this in the calculator. And of course, there are 2 versions of the software. So let's take a look at those a second. So we go to the distributions up here above the vars again. So we have to go second vars. And then we're going to use normal CDF. Whenever it's a continuous distribution, we'll always use the CDF. So we select this one. Now this version of the software has this intermediate step here where it asks us to plug these in this way. And you can see this one is saying -1E99. That is the calculator's version of negative infinity. It's the largest negative number it knows. But what we want is 0.15. The upper one, we're going to just use 10. And these we can just hit enter and then paste. And then we get pretty much the same number we had before, just more significant figures because we are using the calculator instead of the table. And just to show you that those last 2 are optional, I'm going to go second, enter, to bring up the last command. I'm just going to go through here and delete all this other stuff here. So you can see that the mean and the standard deviation are optional. It doesn't matter. So the other version of the software looks a little different, but I mean, once you've seen some of these, you'll be able to figure it out. So same thing, I go second vars, go down to normal CDF, and then this one just waits for an input. So I go 0.15, comma, 10, and then enter, and we get the same thing there. So number 14, it asks us to find the area under the standard normal curve to the left of z equals 0. So we've got our standard normal curve. I'm going to find the area to the left of z equals 0. So we actually already know what this is, right? The area to the left of z equals 0. Well, we know that this is 0.5 here, right? I pointed that out in the table also. The table shows that this is 0.5. But we just know by the way this is set up. We know that z is right in the middle. Half the area is on the left of z equals 0, and the other half is on the right. So it's also 0.5 here. Right, so for this question right here, we don't need a table or a graphing calculator. We know that it's set up 0.5 here, 0.5 here, right? Because the total area is 1. Half of it is to the left of z equals 0, half of it to the right. So what they ask us for the area to the left of z equals 0, we know it's 0.5. Does our calculator know that, however? Well, if we're going to ask our calculator this, we would say normal CDF, and we have lower bound and upper bound. And remember that this is an actual number line here. It's just a regular number line. It goes from negative infinity to infinity. So just like over on the last problem I said we could use a 10 for infinity, we can use a negative 10 for negative infinity. Because a z-score of negative 10, by the time you're out here, remember about negative 3 right here, the curve is almost touching. Now in theory it never touches, but by the time you get out to negative 10, it is so close that our calculator can't tell it's not touching. So negative 10 works just fine for negative infinity. And then the upper bound, of course, is going to be 0. Now if our calculator knows what it's doing, it should say 0.5. So go ahead and punch that in and see if your calculator knows what it's doing. Well, you may be surprised to see that your calculator in this case is close, but the algorithm that it's using times out a little too early, so it puts this little 5 over here. Well, the calculator is just wrong here. It's just not true. That 5 shouldn't be there. So remember, your calculator is really good. It's pretty awesome actually, but it's not perfect. So the answer to this question is exactly 0.5. Now, just out of curiosity, this little 5 here, let's see what happens if we ask the calculator for the area to the right of 0. So in other words, if I ask the calculator, if I go normal CDF, 0 to 10, go ahead and try that once and see what the calculator tells you. Well, there's the 5. If you find out what happened to this 5 right here, because here the calculator says 0.4, and then there's a bunch of 9s, and then that 5. So the calculator is pretty good, but not perfect. It gets both of those wrong. So just kind of be aware of that. That's really the only one that I'm aware of where the calculator is a little off on normal CDF. For the rest of them, if it is off, it's going to be off way back here where it's not going to really matter anyway. So we did, let's see, 20 and 14. So let's try one like number 26. So number 26, we want to find the area underneath the standard normal curve between these two z-scores. So we've got negative 1.40, which would maybe be about right here. Right, negative 1.40, and then 2.03, which would be about here. We're going to find the area right here. So this one's pretty straightforward. We can use normal CDF here. We need the lower bound, negative 1.40, upper bound 2.03. Remember one thing about the number line. On a number line, that's all this is just a real number line. The number on the left is always smaller than the number on the right. So we want the left number first, then the right number. If you get these reversed, it's going to give you a negative answer, which shouldn't make any sense. It should be a red flag. This area under the curve has to be positive. It's going to be between 0 and 1, so you can't get a negative. So make sure you have lower bound than upper bound. And this should give us what we need to know for that one. One thing I should mention too, on the calculator, when there's a negative number, remember, use the negative symbol, right? That's the symbol that looks like this on the last row of the calculator. You don't want to use the subtraction symbol, which is above the add symbol. So make sure you use the negative symbol here. And then you just punch this in and you get something along the lines of 0.8981. I'm just rounding it to the 4th decimal place. You can round it wherever you want to. And here's something that we, in the bad old days before we had a graphing calculator, here's how you'd have to do this one. You'd have to look up this number and in the table that we just saw, it was the left-tailed table. If you'd look up this number, that would give us all of this area, right, including this. Then we look up this number, which would give us this area. Then we would subtract the 2. So it's a little bit more work. With a modern calculator, it's so much easier. We just punch in a couple of z-scores and we get the answer right away. So there's something that's important to notice here. So when you're working on this homework on page 298, the problems that we have been doing, which basically in the homework problems are 13 to 30. So we've been looking at some of these. So this is like number 13 to 30. It says, find the area under the standard normal curve, which is basically what we just did here, right? So 13 to 30, it says that. And then you'll notice it switches the wording from 31 to 50, then it says finding probabilities. So right here is areas, right here is probabilities. They're the same question. They're just transitioning from thinking of the area under the curve to the probability of getting z-scores along this axis, which is really the same question. So we're switching from areas to probabilities. And we're going to answer them the same way. We'll still use the normal CDF command, but it's a good distinction to make because the whole reason we needed this area under this whole curve to be exactly 1 was because we're going to use probability questions. And here's where we make this little transition from area to probability. So for instance, on problem number 32, they don't ask us for areas, but they ask us for probabilities, which is really the same thing. 32 says, what's the probability that z is greater than or equal to 0? So what they're saying is, okay, this picture's not perfect, so you wouldn't actually cross there, but so we've got this standard normal curve. What's the probability that the z-score will be to the right of z, or the probability that the z-score will be greater than or equal to 0? Well, so think of it, this is a number line here, right? And this is some set of data that follows a normal distribution. So if you randomly choose data points, what's the probability that the z-score will be to the right, if z will be greater than or equal to 0? So it's the same question as saying what's the probability that, or what's the area under the curve to the right of z equals 0? The probability that you choose a z-score that's greater than or equal to 0 is going to be 0.5 because half of the curve is to the right of z equals 0. So remember, this is the one that the calculator will get wrong, but this probability is just 0.5. So up here they would have said, what's the area under the curve to the right of z equals 0? Down here they're going to say, what's the probability that z is greater than or equal to 0? And it's the same question. So for instance number 36, number 36 says, what is the probability that z would be less than or equal to 3.20? So what we're going to see later, I think probably the next video I'm going to talk about the difference between continuous and discrete distributions, where with continuous distributions this equal to part doesn't matter. It could say less than or equal to, and if it's a continuous distribution, it won't matter. So we'll see that very soon here. But this question here, the probability that z is less than or equal to 3.20, well, just think about what that's asking. If we have a standard normal curve, and here's our z-scores, so we've got 1, 2, 3. Of course, you have -1, -2, -3. They want to know the probability that z is less than or equal to 3.20. So 3.20, it's like about right here, right? 3.20. The probability that z is less than or equal to 3.20, well, that's going to be a really high probability, right? It's like saying, think about the heights we did. When we did our heights and we got z-scores, if you randomly choose an American, what is the probability that their z-score height is less than or equal to 3.20? Well, it's going to be almost everybody, right? So the probability that z is less than or equal to 3.20 is going to be close to 1. It's going to be a big number. So to do this on the calculator, we could go normal CDF, lower bound, upper bound. Well, the lower bound is a number to the left. Remember, where does this go? Negative infinity, so we could use a -10 here. And there's a little memory hook that you can use. What some students, they get confused about, am I putting a 10 or a negative 10? They have a hard time with the number line. Think of it like this. Doesn't this look like an arrow pointing to the left? Looks like an arrow pointing to the left. On the left of the number line is a negative 10. So it's a little bit of a memory hook that might help. And then the biggest number here is 3.20. And we know it's going to be a number pretty close to 1. And it looks like you get right around 0.9993. Okay, so so 31 to 50, they're going to ask us probabilities about z-scores. We can interpret those as areas under the curve if we would like to, which is how these were interpreted. But they're really just two ways of asking the same question. Remember in the book when it says standard score, if the book says standard score, it's the same as z-score. And again, I've mentioned this a bunch of times, but chapter 6 is a really important chapter for us. So stay right on top of this. Make sure you do the homework for 6.2, and it'll start getting interesting when we get into applications in 6.3. So make sure you're solid on all the 6.2, and ask me about it if you're not sure. And then one more thing I should mention, just as another interpretation here. I was just looking at this number 26. So when we found this, we found the area under the standard normal curve between z equals negative 1.4 and z equals 2.03. Another way you could interpret that through this probability question is, what's the probability that a random American would have a height z-score, a z-score for their height like we did in class, between negative 1.40 and 2.03, about 89.8%, or roughly 90%. So you can interpret the area under the curve as this probability. When they say find the area between z equals negative 1.4 and z equals 2.03, we found that area is 0.8981. We could also interpret that as, what's the probability that if you choose a piece of data from a normal distribution, what's the probability that its z-score will be between negative 1.40 and 2.03? Well, that probability is 0.8981, or in other words, roughly 89.81% chance of that happening. Okay, so go ahead, give 6.2 a shot, and let me know if you have any questions.